Hi, welcome back. In this example, I want to demonstrate what happens to a box if it has a spring and a mass inside of it. So the spring mass system is still a harmonic oscillator, but now it's inside of this box that's accelerating as we drop it from a building or we drop it off the table. And we want to know, does it change the natural frequency of the system? What's happening to this little mass inside the box? So here we can go through our Newtonian mechanics and actually take a look at what's going on. In this example, we have a box. So this box outlined here. That's dropped, so it's accelerating. The whole box is a large box, and then it's accelerating at a constant g, so 9.81 meters per second. And we want to know what's happening to this little mass inside the box that's connected to a spring. So the mass inside the box is 1 kilogram, the spring constant is 2 Newton per meter, and the initial length of the spring is 0.2. So the unstretched length of the spring is 0.2 meters. Initially the system is at rest, so the spring is a little bit stretched, and then it's dropped, and then this MP starts to bounce up and down. So what is x of t? This is a great example of a non-inertial reference frame. So if we pick the origin here, I'm going to call it O prime, and then we've got some ground here, the ground DND, color it in as green. O prime is accelerating. So O prime is not an inertial reference frame. It doesn't mean we can't use it. It just means that we have to account for the total acceleration of the system, not just the acceleration with respect to O prime. I'm going to draw my coordinates like this. My E2 and my E1. The first step is looking at what forces are acting. So we have force of the spring acting up. We have mg acting down. And all that is equal to ma of our mass with respect to an inertial frame. So O, not O prime. So the acceleration of m is going to be equal to my x double dot E1 plus g times E1, because this is acceleration of the mass. It's the acceleration with respect to O prime plus the acceleration of O prime with respect to the ground. So this reference frame is still helping us solve the problem because we can make it a little bit simpler than trying to figure out what the motion of this thing falling with respect to the origin is. But we do need to factor in this total acceleration to an inertial reference frame. So m with respect to O is equal to negative k x minus L0 plus mg. And we're almost at the point where we have an equation of motion. The main thing here is plugging in our values. So mx double dot plus mg is equal to negative k x minus L0 plus mg, or x double dot equals negative k over m x minus L0. Now we have our equation of motion. Because we have a single degree of freedom system, it's just moving up and down. So it does have its x and kind of this total distance away from the Earth, but that's been fixed for us. The motion of O prime, we know that it's accelerating at this g. So that's not a degree of freedom because it's been specified. That's an important point that it might not be obvious at first. That this A O prime O is g E1, so it's not a degree of freedom. Our degree of freedom we can describe as this x. So I like to plug in a dummy variable to get rid of this x minus L0 and say that z is equal to x minus L0, so that my z double dot is equal to x double dot, which means that my equation of motion is now equal to z double dot equals negative k over m times z. And this k over m is equal to 2 Newton per meter over 1 kilogram, or 2. So z double dot equals negative 2 times z. And we've seen this kind of problem before. This is a harmonic oscillator. So take a look at module 1 on how we solve that, but what I know is that z of t is equal to some amplitude times cosine root 2 t plus another amplitude times sine of root 2 times t, where omega equals root 2. And this is our natural frequency. So we're going to show two scenarios: before t equals 0 and after t equals 0. So before t equals 0, A equals 0, and then also A of O prime with respect to O is equal to 0. So the whole box is not moving at all, which means that we have AM equals 0 E1 plus x double dot E1, which is equal to negative k times x minus L0 plus mg. And this is equal to 0, so really what we're doing is just relating the force of gravity to that force of the spring. So 0 equals negative k x minus L0 plus mg. So x of 0, solving for x, is equal to L0 plus mg over k. What this is my initial condition. I need two initial conditions. One is that x of 0 is this, and then the second one is that v of 0 is 0, since it was released from rest. Now I can plug this into my equation for z, because I know that it's some a cosine root 2 times t, root 2 t, plus b sine root 2 t. And here I'll plug in these values. This is 0.2 plus 1 kilogram times 9.81 meter per second squared all over 2 Newton per meter, or 5.11 meters. So z at 0, now we're over here at after, so when t is more than or equal to 0, this is equal to 5.11 minus L0, which is equal to 4.91 meters, which is equal to a cosine root 2 times 0 plus b sine root 2 times 0. So a equals 4.91. That's plugging in for my first initial condition, and then I can say that z dot of 0 is equal to 0, and this is equal to b. So my final equation, I have a z of t is equal to 4.91 cosine root 2 times t. And if I want to plug in for x of t, then I can just say that it's z of t plus L0, or 4.91 cosine root 2 times t plus 0.2 meters. And that is my final x of t, so figuring out what the motion of this system is after it's released from rest.